We begin by generating a blank image of any size. We will then generate a grid over top that image, assigning each corner a random vector called a gradient vector. We now select a pixel on the image where we can take its image coordinates and calculate the corresponding cell of our grid that that pixel inhabits. So this can then be used to calculate the pixel's position within that cell, what we'll call the pixel's cell UV. We then calculate a vector going from a corner of the cell to the cell UV using both the cell UV and corner coordinates. We then repeat this for the other corners of our cell. Now, with our 4 corner vectors, we get a dot product between a corner vector and the gradient vector of its respective corner. Once more, we repeat this process for the other 3 corners, giving us 4 dot products, 1 for each corner. Now we're going to interpolate horizontally between our dot products using a smooth step function, plugging in the left and right values as inputs and the cell UV's x value as time, allowing us to solve for our interpolated value. We then repeat this with the other 2 dot products, leaving us with 2 values. With these values, we further interpolate between them, plugging in the values as inputs and the cell UV's y value as time. This outputs the final grayscale value of our pixel. We now repeat this process for every other pixel within our image, generating our Perlin noise. You may notice, however, that the final result still looks off, and this is because the resulting values of our pixels lie between -1 and 1. And since the pixel will be black at any value at or below 0, there is an inherent bias towards darker values. We can fix this discrepancy by multiplying the pixel's value by 0.5 and adding 0.5, having the final value range between 0 and 1 instead, brightening up the final result.